class. Okay, here you go. Today is the 25th of September. And I'm gonna finish chapter 2 on 1D motion. And we're going to start vectors, which is going to be chapter 1. It's like going back here to chapter 1. And I'm organizing this course. It's slightly different from the book, okay? In this book, they first introduce you to vectors, and then they work with vectors from the very beginning. What I'm doing, I introduce vectors only when it's needed. And now we're about to come to the point where vectors is needed. When we are dealing with one-dimensional motion, we do not need the vectors at all. Okay, and how is this book organized? This book is organized in a way that very few books are organized. Most books, like I said, they start with one-dimensional motion. And because we're dealing with one-dimensional motion, there's no need for vectors. And then when we get to two-dimensional motion, then we introduce the concept of vectors. So what this book does is he introduces the concept of vectors right in the first chapter, like here 1.5, and then he treats one-dimensional motion with vectors. That's what he does. Okay. I think the other way is better. Okay, and now where are we right now? We are right in here, free falling bodies. I covered displacement, speed and velocity, acceleration, equations of kinematics for constant acceleration, right? Applications of equations of kinematics, right in here. We look at the graphical analysis of velocity and acceleration. And now we're going to look at freely falling bodies, which is nothing but a special case of uniform acceleration. So far, I'm going to document that for you, show what we have covered so far. Which chapters we have covered so far. That's Monday. So far, we covered the following chapters in the book. This chapter 1.2, which units. Don't want like that. Chapter 1. 1.2 units. Yeah, scalar and vector. That's all we cover in chapter 1 so far. And very soon we are going to be covering more of chapter 1. Chapter 2. Here's section 1.2 units. In chapter 2, we covered sections 2.1 2.2, 2.3, 2.4, 2.5, and 2.7. Today we will cover 2.6. Okay? And today I expect to start, right? I expect to start sections. Oops. Sections 1.5. 1.6, 1.7, 1.8. Okay, at least 1.5, 1 and 1.6. Maybe we'll have time for the other ones. If you don't have it, we continue next time, okay? Next lecture meeting. Oh, and don't forget, right? Very important. Here you go, here's the schedule, all right? We're gonna have an exam next week, Wednesday next week, chapter 1 and 2. And the things that we have covered for lab 1. And by what do I mean by lab 1, you know, you go cell graphs, CL, right, which is not in the book, measurements, CL and measurements, and sig figs and results, sig figs of measurement, right? Let's put this way, sig figs of measurements, sig figs of results. Okay, so you should expect everything up to this point. Everything up to, let's see. Yeah. Of course, don't include 4 and 5, right? Don't include 4 and 5. Let's see, up to material, material up to 27, excluding there's 3 and 4. 3 and 4, like that. More students coming in. See if we have any. 5. Okay. And that's what we have so far. Now let's start talking about free fall motion. Example is nothing, free fall motion is nothing but a special case of uniformly accelerated motion. It's nothing but that. If you learn uniformly accelerated motion, you will understand free fall motion. You will understand free fall motion, okay? A special case of uniform acceleration motion for a equal to 10 meters per second square. Well, strictly speaking, it's 9.8, okay? But to simplify calculations, we usually use 10 meters per second square. It's no big deal because it introduces only a 2% error in the in the final result. That's what free fall motion is all about. A special case of uniformly accelerated motion for acceleration equal to 9.8 meters per second squared. The situation is like that. Here you go. And I'm going to do step by step here. Galileo Galilei studied this type of motion during his time. And today we still remember him because of that. Okay, so suppose that you have a building, right? That's just like that. And at the top of the building, you have this object that you're going to release from the top. And release from the top means what? The initial velocity, I'm going to point here. The initial velocity is going to be equal to 0. That's what releasing, right, from the top means. Equal to 0. Okay. Yo, wrong place. And by, at this instant of time correspond to t equal to 0. Okay. I don't need that anymore. So that's the definition of accelerated motion. That's the definition of free fall motion. Whenever the acceleration of the object is uniform at a value approximately equal to 10 meters per second squared. Okay, but let's not forget 1D, right? I'm gonna write that down. 1D free fall motion. The case of one-dimensional. And when we solve this problem, in order to solve this problem, what we have to do, we do what we always do in physics, right? Here, we come up with a drawing of the situation to have a picture, a mental picture, not just a mental picture, but a physical picture in the paper, in the medium. The medium can be paper, can be electronic medium, whatever, right? We illustrate the object, we put the initial conditions, and the next step would be to put the axis of motion like we have right here. In this case, I have decided to put my axis in the upward direction. I'm going to put next to the edge of the building, a little bit more. Otherwise, you don't see the edge of the building, right? Here you go. This is the y-axis. Okay. I'm going to label the y-axis, just like I labeled here. I'm going also, show, I'm also going to document the initial height of the object. Right here on the left side. Someone else is coming in. We have to go through all this trouble, okay? Don't try to solve this problem mentally without doing any drawings. We have to have this picture, this physical picture in any type of medium so you can keep track what's going on. And then I decide as well to put the origin. No, I can put the origin wherever I want, but in this case, I'm deciding to put the origin at the bottom of the building. So, building, particle, initial velocity, initial instant of time, axis, label the axis, initial position of the particle, that's correspond to the origin of the axis. And I'm going to take advantage and by origin, erase it. I'm putting the 0 right in here. What else can we do? Well, and now we have to illustrate the acceleration of the object as well, okay? And that's what I'm doing here. Instead of putting G, I'm gonna put A for the acceleration, which by the way is represented by the letter G, right? And G means 10 meters per second square. What's happening here is this arrow. What does this arrow represent? Okay, this arrow that you see here represents the direction of the acceleration. Okay, it means that the velocity of the particle is increasing as it's moving down. Increasing as it moves down, increasing, okay? That's what it means. Because the acceleration is pointing in a direction opposite to the direction of the y-axis, we do more. We come up with a negative sign for this G, okay? Because it's in a direction opposite to the axis. Superscript. Okay, and right in here. And by the way, I have to put a negative sign here as well. G is said, the letter G is always going to be positive, okay? The acceleration of gravity. G is always represent the symbol G is always represented to be positive. And the negative sign in this case comes about because I have chosen the y-axis to be upwards. If I have chosen a y-axis to be downwards, right, it's possible to do that because axis we can choose in any direction we want. Suppose that I have chosen the y-axis to be downwards, okay? In this case, it would be y prime. Y prime. Oops, didn't do it. Ooh. Okay, got it. Now, y. Then the G, the acceleration would be positive, not negative. Okay? And we can solve problems with this type of axis as well. But let's stick to this one, that's the easiest one. Everybody's more familiar with an upward axis. Okay. So let's play the movie again, right? All right, here you go. Point particle, initial velocity, initial instant of time, y-axis, initial position of the particle along the axis. That's the origin of the axis. That's the acceleration of the particle. The acceleration is downwards. Okay. And what acceleration downwards mean? Well, it means that a little bit later on, the particle is going to be, let's say, right in here. Okay. And then a little bit later on, the same particle, because it is accelerated, okay, is going to increase its distance from the previous one a little bit later on. is going to be even further away. It's uniformly accelerated, right? And so on. Okay, and so on. Let's say here is t equal to t0, t1, t2, t3, right? So here you go. I'm going to play the movie, right, for you. The particle is no longer here, right? Now it's here. Here you go. First position, next position. Next position is going to be this one. That's a motion diagram, remember? That's a motion diagram for a free falling particle. Let's see, I move that. Yeah. Better now, right? Yeah. And the final position right here. Yep, here you go. Okay. And how do we? So let's write it down here. Okay. On the okay. To solve this type of problem, we start by drawing the situation of the problem, right? To solve this type of problem. To solve this problem, we do an illustration. We make an illustration, right? We make an illustration. First, we draw a building, right? Building to the particle. First, we draw one, a building. We draw a building first. We draw a building, the particle, initially at rest. The acceleration, I'm gonna put that vector, right? The direction of the acceleration of the particle. The building, oh, wait a minute, the particle, okay, the axis, right? Forget it here. The vertical axis, and label it the direction of the acceleration of the particle. And what you think is going to be the motion diagram of the particle. 6. Then we can start doing what really matters. Oh, well done. We can start, not what really matters, but then we can start writing down the equations of motion of the particle. In this case, the acceleration, because I choose an upward axis, vertical axis, let's put here an upward vertical axis. It could have been a downward as well. It could have been a downward as well. Right? Label the axis, the direction of the acceleration of the particle. Then we can write down the equation of motion of the particle. go back to our equations of motion for uniform acceleration. Let's go back there. All I have to do is to copy what I did there before he go. And remember, we are going to have this special case in which the acceleration is constant, right? But it has a specific value. And this value in our case is going to be minus g, which represents minus 10 meters per second square. Minus 10 meters per second square right here. Right? The velocity is v naught plus at. Okay, and we are going to simplify that. V naught, we already know that's 0 for that special case. And the acceleration, we just substitute the value, put minus 10 meters per second square. Our axis is not going to be y-axis, it's not going to be x-axis, it's going to be my y-axis. So all I have to do here is to exchange x to y, okay? And then we use everything else that we know to be the value. We do not have this initial term here, but we do have minus 10 meters per second square here. I'm gonna put between parentheses, right? And we end up getting minus 5 meters per second square because we have this half here to cancel the 10, to simplify the 10 upwards. I still didn't give you a value for y naught, okay? I still didn't give you a value for y naught, but let's say y naught is 20 meters. Suppose you're at the top of a building, that y naught is 20 meters. How long? You know, so we're gonna do like that, okay? Example, right? Let's treat that as an example, gosh. That's so, example, right? Example. Let's put this example down here. Example. Example. So you are at the top of a 20-meter high building. How long does it take at the top of 20-meter high building, and you release a particle from its top? How long does it take? Does it take for the particle to reach the floor? Huh? Solution, right? You know, I'm going to do here the genetic way, right, of setting up this problem. So here's the genetic way. Here you go, right? I'm not going to put the numeric values here yet because I want the most genetic way of expressing this equation. Okay, it's like that. And we're doing an example. Okay, here becomes 20 meters now. Here it becomes 20 meters. Right? And we have this equation now for the position 3. reach the ground, not the floor, but the ground, right? At y equal to 0. The ground is set at being at y equal to 0. So what we have to do? We have to make y equal to 0 here. Right? So here we go. Y equal to 0, we solve for t. That's what that's the problem. That's what the problem is asking. So I'm going to put like that. A. How long does it take for the particle to reach the ground? Solution, item A, right? Item A. In the next step, we make this an equality, right? What else can we do in the next step? We can cancel the meter on the left side and the meter on the right side. When you cancel the meter, we end up with 1 here. But if I want to, make it look nicer, just put the 5 in the place of the 1. And we are almost done with the solution of this equation. Okay. It's a quadratic equation. 5, second square goes upstairs on the other side, and then you divide by 5. This ratio becomes 4 second square, right? 20 divided by 5 is 4. And now we can solve for t. T becomes what? 2 seconds. It takes 2 seconds for a particle to reach the floor in a building that's 20 meters tall. That's one type of problem that you're going to see. I can come up with a second type of problem, and another part for this problem, right? What is the speed of the particle? The speed of the particle just before hitting the ground. Just before hitting the ground. Item B. Item B here. In order to find that, we have to use this equation here. Even better, what is the velocity, right? Velocity of the particle. Let's just before hitting the ground, use this, this equation here. It's 2 seconds, right? You replace 2 seconds here in the position for the t. And what they're going to get? You're going to get minus 20 meters per second. Okay? That's the final velocity just before hitting the ground. For every second, don't forget, for every second, the speed, the velocity increases / decreases, right? By 10 meters per second. The velocity decreases by 10 meters per second. Depending on the direction of your axis. In this case, the velocity is decreasing because it's becoming more negative. In this case, okay? In this case, the velocity is decreasing because it is becoming more negative. Also, in this case, the speed is increasing because the magnitude of V is increasing, right? That's an important difference between speed and velocity. if velocity is minus 20 meters per second, you know, the speed is going to be plus 20 meters per second. Important difference between speed and velocity. This negative sign of the velocity implies that the direction of motion, right? Implies the direction of motion here is downwards. That's what this negative means, instead of upwards. So here we go. And we represent this direction of motion as this arrow, as this downward arrow. And notice that the direction of the velocity coincides with the direction of the acceleration. Okay, it's not always this way. That's how we represent, and I don't need that anymore. I don't need this one anymore. I don't need this one. I'll keep this one for now. Okay. I'll keep this one for now, and we're going to look at another problem. Building. Okay, so there are all sorts of problems that we can solve. Okay, let me write it down here. So here you go. There are all sorts of problems we can solve. All sorts of free falling problem that we can solve. We just look at one of them. Okay, one is how long it takes for the particle to reach the ground, right? We did that. Check.
Professor,
Right?
I have a question.
Yes.
So the initial velocity was 0 from this problem?
Uh-huh.
Oh, okay.
In this problem, the initial velocity was 0, yes. And is it spelled out here, right? Did I put it here? You release, yeah. You release. Since you released, V naught is equal to 0. V naught is equal to 0.
Oh, okay. Thank you.
Okay, so that's okay, so that's one type of problem. There are all sorts of free falling problems that also there are all sorts of free falling problems that you can solve. How long it takes? How long does it take? Let's take, right, for the particle to reach the ground. That's one way. Okay. What is the final velocity of the particle, right? Okay. What else? You know, given the amount, that's another type of problem that we can solve. Given the amount of time it takes for a particle to reach the ground, comma, find the initial height. Okay? Find the initial height. Those two, you already did that. So this one has a very important practical application. This one has a very important practical application. Suppose that you're at the top of a building and you want to know the height of the building. Okay? This one has a very important part. Let's write it down. This one, he has a very important practical application, right? Suppose you are at the top of a building and you want to know its height. What can you do? What can you do to determine the height. What can you do to determine its height, right? The height of the building. You're going to do that, right? So here we go. Another example. Let's put it here, example 1. Now, example 2. You are at the top of a building. You're at the top of a building. The top of a building. And you do not know it. You're at the top of a building that you want to determine its height. You release a little stone from the top and time how long it takes for the stone to reach the ground. Okay? Time, how long it takes for the stone to reach the ground, and determine this amount of time to be t equal to 20 seconds. Building. Neglecting air friction. Air friction. What is the height of this building, right? What's the height of this building? So you must have a timepiece, right? You have to have a little stone or any other object that's heavy enough. You're not going to release a piece of paper because a piece of paper is going to encounter air friction along the way. But a stone would do a good job, right? The moment you release, you start your timer. Keep on watching your stone until it hits the ground. When it hits the ground, you stop your timer. Okay?
Professor, I have a question.
Yeah.
More the heavier object, you drop it from the high ground. There's no air friction.
Yeah, what was the question?
So okay, let's say more you drop the heavier items from the high ground, the air friction gets reduced, or just there's no air friction gets no I mean there's no air restrictions and stuff.
Yeah, this problem we're going to treat later on. Okay, this
Uh-huh.
problem is a little bit more complicated. It requires some other background information that I didn't give to you, but just assume that at this moment, okay, there is no air friction, that the
Oh,
friction
okay.
is negligible, okay? But yeah, we're going to treat this problem later on when we start with Newton's law, okay? But
Okay.
hold on to that, okay? And okay, so neglecting air friction. In order to solve this problem, in order to answer this question that you're asking, we need the concept of weight, okay? The concept of force and Newton's law. So hold on to that for now, okay? And then we are going to, and let's go back to this example, right? Neglecting air friction was the height of the building, right? You time it to be 20 seconds, right? Solution. So this situation is like the drawing that you saw right here. It's the initial height that you do not know, the initial height. And you time it 20 seconds from here to here. Okay, let's put together our equations and let's see if we can solve our problem. Our equations are those. Maybe we should put another one as well. No, those two are enough. I don't know. Okay. Okay, you already know that this one is going to be minus 10 meters per second square, right? You know that this one is going to be 0. The is going to be 0. And here it's going to be 10 meters per second square as well. Like that. This is the one that we want to know. This is the one we want to know. And this one here, don't forget, we know what t is, right? T is 20 seconds. But if we do that, we just determine the velocity, the final velocity. We don't want to determine the final velocity. We want to determine the height of the building, which is y naught. This term goes to 0 because the initial velocity is 0, right? And here we end up with minus 5 meters per second square. I think I need to put that. Let me do the following. I'll copy this one here. Okay. Let's do this way. Like that, right? Minus 10 meters. And I can put the t later on. So what we want to find now is this guy here, right? And it's not 20 meters. We do not know, right? But we do know what t is. 20 seconds. Okay. Just like a recipe, right? And then it becomes minus 5. This one becomes 400 seconds square. Right? We can go ahead and simplify as much as we can. Second square cancels the second square, so all this left is meters. 400 times 5 becomes 2,000. Okay, and then we get this equation here. Don't forget this y here means the final position. The final position, by the way, you already know that's going to be 0 the moment that the stone, the object hit the ground, right? Man, we are getting a very high building here. See that? 2 kilometers high building. Okay, that's what we are getting here. Let's see what's the tallest building. So 20 seconds is too much, right? It's not realistic, the value that I use. Let's take a look at the tallest building in the world. The world, 828 meters. There's no 2,000 meter high. Well, it can be a tower, right? It's not a building. No, you don't get, you may not get a building that's 2,000 meters high, but you can get a tower, right? Let's take a look. Tallest tower in the world. Towers are easy, don't you have? Let's see, tallest tower in the world today. Let's see. Oh yeah. They still consider the building a tower. That's the one there in Dubai. Okay, but that's an example of how we can use this equation to solve problems, right? To solve real life problems. Okay. And then there are other types of problems too. Here you go. What if we, instead of releasing the stone, what if we initially propel it upwards or downwards, right? Or downwards with an initial velocity. You can have something like that. Okay. We can have problems like that as well. For instance, right? What's the maximum height reached by a particle that is propelled upwards with a velocity of 20 meters per second? Right? That's one possible, that's one, that's another type of problem that you can start thinking about. Okay. Or you can, or repeat example 1 for a initial upward velocity of 20 meters per second. That's another, or another one. Repeat example 1 for initial downward velocity, right? All sorts of problems that we can come up with. And so on, right? And so on. Okay, and you can come up with those diagrams, right? Just like those ones here that I did for you. Let's see, motion diagrams, right? We can, let me do a motion diagram here. First I did the movie, right? Now let's do a motion diagram. This one here. Here you go. One snapshot of the motion diagram. That's going to be another snapshot of the motion diagram. And then one more motion diagram here. Another snapshot of the motion diagram, right? Downwards, the distance increases. But if you have the case of a particle being initially, propelled upwards, the distance is going to decrease, right? Because the speed of the particle is going to decrease. The acceleration is downwards, but the velocity is going to be upwards. Let's do this motion diagram. Oh, here we go. One here. Okay, now it's going to be different. I need that. Okay, I need this one here. We did that. But now we are going to propel the particle upwards at 20 meters per second. Right? Here you go. And I'm going to put my velocity vector, initial velocity vector upwards. Just like I did in the other one. Yeah, I put on the side, right? So let me put on the side as well. What's going to happen to the motion of this particle? In the next step is going to, move a big distance, right? Because the velocity is going to move a given distance. with it. And after some time, it's going to be a smaller velocity here at this spot. In the next instant, okay, it's going to be a smaller distance, right? Until the particle reaches its maximum height, and it's going to be instantaneously at rest. At this point, it's going to be instantaneous at rest, and then it's going to fall back. And it's going to fall back in the same way that it went up. I'm just putting here on this on the right, this place to the right. This one here is like that. Right? And then finally, it will keep on moving downwards since it's 20 meters per second, right? The distance that it is going to displace is going to be longer than this distance that you see here. Likewise, the next distance it's going to display is going to be, the next displacement is going to be more. Than before. That will be the motion diagram. This arrow here, which represents the velocity of the particle, right? As the particle moves up, the speed, right, decreases, right? So we can represent by this arrow, by this shorter arrow. The next arrow is going to be even shorter, right? That's a nice representation of the velocity. And then on the way down, now those are the concept, where I'm starting to use the concepts of vectors here. So you can get familiar with that right now. Size and position, let's see, format, shape. And now, let's see. This one? Yeah. Here is going to be downwards as well. But it's going to be shorter, right? Here, next one is going to be even shorter. Should be the same length as the other one that I put on the left side. If the particle here is at rest, the representation here is going to be just a dot. Just a little bit. But then what's happening for the other ones? This one is going to be longer. And the next one is going to be even longer. Okay. The acceleration, I'm going to put a different color. So you understand that's going to be a different quantity, right? That's the initial velocity. This initial velocity upwards. And 9:50 right now. Any questions before we move for the break? So that's what free fall motion is all about. The steady type of motion. At that time, he was rather successful. Before Galileo Galilei, there was this other guy that studied this type of motion as well, and his name was Leonardo da Vinci. Leonardo da Vinci also attacked this problem, but he was not as successful as Galileo Galilei himself. And that was during the Renaissance, when Europe was moving, was exiting, right? The Middle Ages. Meter, we go seconds. Let's take attendance now. Today is the 25th. Sky, are you there? I don't see Sky here. Next is Tessa. Are you there, Tessa?
Yeah, I'm here.
Okay, thank you. Destiny,
I'm here.
thank you. Gael Garcia. Let's see if I can get the. I don't hear from Gael. I'm going to put a star here in his attendance. Next is going to be Jason, right? Read on Jason. Okay, thank you, Ridwan. Next, Ashley is Zoom. I don't see Ashley here. Norberto Lopez. Thank you, Norberto. Anabel Madrigal.
I'm here.
Thank you. Eric Martinez. I don't see Eric here. Okay, so we go. Vanessa Mena.
Here.
Thank you. Nazmoon. Nazmoon didn't show up anymore, right? Catherine Pacheco. Thank you, Catherine. Camden Park.
Yes, I'm here, Professor.
Thank you. Victoria Preciado. I don't see Victoria here. See. So far we have 8. Alexis Richardson.
Here.
Thank you. Donovan not here, right? One more is Marco Sanchez. Okay, we have 10. Okay, 11 with Gael. Okay, so 9:55 right now. To 10 a.m. Okay, so see you shortly. Stop sharing. Hello, folks. I'm back here. A little bit late. Okay, so let's see. Okay, so we ended the part on one-dimensional motion. We finished. Okay, we're done with 1D motion. And now we will start vectors. Okay. At this point, you should already have a qualitative idea of vector. So going back here, see this particle here is moving downwards, right? So we say that we have a vector velocity. The vector velocity of this particle at this point is going to be downwards. The acceleration also changes the velocity in a downward fashion. So if you have a vector velocity upward, what does it mean? It means that the magnitude of this arrow or this vector is going to decrease. However, if the vector velocity changes direction as being downward as time goes by, the length of this vector increases, okay? And that is exactly what you're seeing here. The acceleration affects the velocity. And vector is a mathematical quantity. Let's write that down here first. Okay, vector is a mathematical tool used to solve many problems, many real life problems in a much simpler way. Okay? By the same token, we invented the concept of numbers, right? Numbers. We also invented this concept of vectors. I like to tell my students tell my students I like to tell my students that vectors are a type of number, okay? A type of number that has an additional piece of information, okay? Real life. Whereas numbers tells you the magnitude of something, vectors have a vector, right? A vector has information on the magnitude and direction of something. Just like you had here in the case of the velocity vector, right? The magnitude of the velocity vector is represented by the length of this arrow, and the direction of the velocity vector is represented by the arrow as well, in which way the arrow is oriented. Here we have the same thing for acceleration. The magnitude of acceleration is represented by its length, and the tip of the arrow represents the direction of the vector, in which direction the vector acceleration is. Okay? Not every physical quantity is a vector. Not everyone is a vector. Okay, and then it comes to a point. Then we came to a point where we must revisit the three core principles of physics. We must revisit the three core principles of physics. Let's go back here. Primary definitions. Okay, right here. Here you go. Remember the three core principles of physics? Come to a point. And there is a very important distinction between basic quantities and primary definitions, okay? Lengths, all those basic definitions that we have, they are not vectors, okay? Those quantities which are not vectors, length, time, mass, which are represented only by a number, by a magnitude, we call it, they are scalar quantities. They're called scalar quantities. Okay. Vectors distinguish from scalars and numbers okay? By that matter, and numbers by that matter, by this matter. So scalars versus vectors, right? Scalars versus vectors. Scalars are represented only by a magnitude, by a number that is always positive. So length is a scalar. Is a positive quantity, right? It's a positive quantity. Time is a positive quantity. Mass is also positive. And none of these quantities have a direction. Length, time, and mass are positive quantities. And none of them, all right? None of them have a direction. Okay? But wait a minute. But those primary definitions, position and force, those are vectorial quantities. Those are vectorial quantities. See the distinction? From basic quantities to primary definitions? I can tell you right now, let's make a list. Let's start make a list. Let us start to make a list of scalar and vectorial quantities. Okay. Well, I already told you that scalars, length, time, mass. We already know that. But there is more. There is more. Distance. Distance is a scalar quantity because it doesn't have a direction. And also speed. Those are all scalar quantities. And then we have the vectorial quantities. Vectors, scalars and vectors. Okay? I already told you that position is a vector. And force also is a vector. They all require a definition in terms of direction, right? In the case of a position, let's go back to our axis right in here. Okay, the position of this particle right in here in this axis can be represented by a vector that goes from the origin to the point where the particle is located. Okay, so that's the position vector of the particle. And I'm going to see if I can get one good one. Say, yeah, here you go. I'm gonna use those, okay? Vectors, now we're talking about vectors here. Okay, so I'm gonna modify this slightly. Okay, so let's say that's the initial position. X naught is the initial position of this particle, right? I'm not gonna get into this one yet. You know, the initial position of this particle can be represented by this vector here, and the vector position goes from the origin of your system of coordinate, or your coordinate system, to the point where the particle is located. Okay? Vector position. Vector positions we usually represent by the letter. You know, let's go back here. By the letter R. R, and by the way, there is one more thing that you have to know about vectors. Insert equation. Okay, like that. We usually put a arrow at the top of the letter. Okay. Anything that has an arrow there at the top of the letter should be considered a vector. That's the notation for vector. There's another one. There's another notation for vector. Either, you know, the arrow at the top or the letter in boldface. It's easier for books. Many books represent a vector by a bold-faced letter. And your book is using this bold-faced representation of a vector. Okay. In the case of force, we use the letter F, or, you know, the bold-faced letter F. Let's take a look at the notation that the book used. This one right in here. Chapter 1, scalars and vectors, right in here. That's 1.5. Okay, so, oh, see here? Representation. I think I had seen also bold-faced notation here. No, I don't have. Well, we do have bold-faced somewhere down there. Oh yeah, bold-faced with an arrow. Yeah, okay. They are putting an arrow in the bold-face, but some books use just the bold-face without the arrow there at the top. Okay. That's the notation that I use. And let me see, I think that I saw them using just the bold-face notation here. Let's take a look, let's take a look. No, yeah, okay. Yeah, they use the bold-face with the arrow there at the top. But some books, when they put the bold-faced, you know, they exclude the arrow at the top of the bold-faced letter. Okay? I prefer this notation here. I prefer this notation here with the arrow there at the top. Position and force, they are both vectors. And then there are more. There are more. Remember the displacement. Displacement is a vector too. And the displacement is defined the same way that we define it as a scalar, right? As a scalar in one dimension. You know, remember displacement delta x in one dimension. I'm not gonna put boldface here. Here you go. Delta X was final position minus initial position. But now we also have the displacement vector. The displacement vector we represented as being final position minus initial position. Okay? And I'm gonna put it delta R here. Which other definition did we come up with? Let's take a look at the definitions before, right? Let's take a look at the definition that we came up in kinematics. I was making a list, primary definitions, secondary definitions, and so on. Here you go. Right? Displacement. Okay, here you go. So I'm gonna copy and paste it here. Okay, here you go. Position, displacement, then we define the average velocity, right? Then now, after average velocity, we define instantaneous velocity. After instantaneous velocity, we define average acceleration. And after average acceleration, we define instantaneous acceleration. All those quantities, all those definitions, they are vectorial in nature. Okay? Average velocity, we define the average velocity vector, we define the same way that we define the one-dimensional velocity, right? Here you go, the average velocity, PAVG, equal delta X over delta T, like that. Now my average velocity vector is going to be defined as like that. Is going to be my delta R over delta T, right? And the instantaneous velocity vector is going to be likewise the limit, right? Instantaneous velocity vector, the limit in which right here, this one here. Yeah, the limit. I don't need that. Delta R and delta T simultaneously goes to 0. One is a vector, the other is a scalar. Instantaneous velocity. And what's next? Average acceleration, right? Average acceleration is going to be final velocity minus initial velocity vector, and so on. Okay, Well, let's take a look at the representations, right? You already saw the one-dimensional representation of position. That's the initial position vector. This one here, I'm going to represent the final position vector. I don't even need those numbers here. I don't need that. But that's a one-dimensional case. That's the one-dimensional case. Okay, I don't need that yet. I don't like that. Let's see, this one goes to the bottom. Okay, and then I'm gonna put something else here. I'm gonna copy this guy. Okay, I'm gonna paste there. Right here. I'm gonna make it like larger as well. So it's easier to see, right? That's the vector position. The initial vector position. I'm gonna put the initial there. Let's get black here. No. Good. Initial. And then we have the final position vector. And then if I want to represent the delta x, the displacement is going to be represented by the following vector. By the vector that goes from the initial position to the final position. Okay, so I will get this one here. Paste here and write that down. Yeah, delta R equal to final position. Oops. Not good, not good. Let's see. Okay, now we can get it right. Okay. Final position minus initial position. Can you understand that? I'm going to overlap the final position vector and the initial position vector with the displacement vector. But don't forget that just the one-dimensional case. We're going to extend that to the 2- and 3-dimensional cases very soon. I don't need that. Okay, here we go. Initial position vector, final position vector. That's going to be the final position vector, right? But remember that I want the minus, wait a minute, yeah, initial position. That's the initial position vector, right? Wait a minute. No, that's the initial. This one's supposed to be the final. Yeah, final position vector, right? We want to sum this vector here with the negative of this vector here. The negative of this vector here is represented by an arrow pointing in the other direction, like that. So what does it mean? I just invert the direction of the arrow here. Okay, and I'm going to increase the size. Yeah, let's increase the size. Everything here, I like the other one, the other tip better. Here you go. That's the tip that I like better. Okay. So if I want to sum this vector here, if with this vector here, which is the negative of the other one, there is a very special way of doing that. Okay, and it's going to be this way. Here you go. Let's get that. This one right here. I don't need that anymore. Okay. Is what we call notice that we have this difference here between those two vectors. So the resulting delta R vector is going to be exactly what you saw here. Okay, the beginning of one vector until the end of the other one. Okay, that's what we call the head to tail method in one dimension. It's going to be this guy, plus, this other one here. The head to tail method works this way. Put a little bit more to the right, okay? And then what is left is going to be this resulting vector here. Make sense? You walk to the right and then you walk to the left, but you walk to the left a larger distance. Consequently, your displacement is going to be from the beginning of the final vector to the end of the initial vector. Okay? That's how we can interpret the summation and subtraction of vectors in the one dimension, okay? So let's work in a more generic way. Now, here you go. Here I have representation of a vector, generic vector A. This generic vector A has an angle theta with respect to the horizontal direction, that we also call the x direction, okay? Properties, right? Let's talk about properties of vector. We're going to see an important property of the vector is that it doesn't matter where the vector is located here in the plane. If I go ahead and draw a second vector that has the same length and the same direction, it doesn't matter if I put them in a different spot in my XY plane. This vector here is going to be equal to this vector, okay? Why is that? Because vectors carry information only about the magnitude and direction. Let's write it down. So here you go. Vectors, properties of vectors. One, vectors carry information only about their magnitude and direction. Consequently, it does not matter where you place a vector in the three-dimensional space, okay? In the three-dimensional space. If you have two vectors, A and B, of same magnitude and direction placed at different points in the 3D space, okay? These vectors are still considered, these vectors are considered the same. Okay, so we go. That's what this illustration means in terms of words, right? What else? Okay, and this illustrates something else. This illustrates that vectors can be multiplied, not just multiplied, but also divided by scalars, okay? Vectors can be multiplied and divided by scalars. In this case, the vector A was multiplied by the number or scalar 2, which ended up being A plus A, okay? So that's something else that we have to take into account, consider. Vectors can be multiplied and divided by scalars. For instance, the 2A, let's see, I'm gonna put like that. For instance, the 2A vector is nothing but A plus A vector. The A plus A vector. Okay? Mathematically speaking, 2A is equal or 2A is equal to A plus A. Graphically speaking, it's going to be something like that. You get the vector A twice, put the tail of one at the head of the other, and the resulting vector goes from its tail to the head of the other. Okay? The vector A is different from the vector 2A, very important. I'm going to put it a little bit to the right. Okay, and I'm gonna rotate like that to make sure that those two vectors start at the same place, right? This one is going to start a little bit more to the right. This one too. This one is start a little bit more to the right, like that. Like that. Beginning of one of the vectors, end of the other one. Make it look nicer here. Here goes this one too. This other one. Okay. So here you go. Alpha, beta, gamma are, we don't have to worry about those alpha, beta, gamma. Those two vectors that you see here, although they point in the same direction, they have different magnitudes. Consequently, they're different of each other. That's what I mean here, right? This vector here, in this case, A is different of B. Like that. Okay, here's They both make an angle theta with the horizontal, but they're different because their magnitude is different. Okay. Vectors, here you go. I'm gonna write that down here. Exactly. Okay. Vectors of same direction and but distinct magnitude are different of each other. Okay. And 57. Let's see if you have something else before I go. Any questions so far? We're gonna get into a break very soon. Okay, this vector here that you see, you know, I'm going to get, here you go. I'm gonna get this vector, copy and paste. Okay. And I'm generating another vector that has the same magnitude. And then I'm going to do the following. I'm going to rotate this vector. I'm going to rotate this vector, let's say 90 degrees. Okay. And then I'm going to call this vector vector C. I don't need that anymore. But I am going to put it here. Okay. Notice, oh, overlapping there, right? Yeah, let's put it back here. You know, this vector here has a different direction, but has the same magnitude, right? Has the same magnitude, and it's still different from the other. So that's another property of vectors, right? Having vectors, okay. Likewise, vectors with the same magnitude, vectors with the same magnitude, but different directions, are also distinct of each other, are also different of each other. Okay. Going back here, right? If you had A different of B, we also have that A is different of C. I'm gonna A different of B and A different of C. Okay. So let's take our break now. 10:59. Any questions before we move forward? So I'm going to see. No, okay, thank you. So let's take our break from 11 a.m. to 11:15 a.m. Okay. I'm gonna save it here. And I see you in 15 minutes. Okay, so going back here. So the A is different of B, A is different of C. Even though B has the same direction as A and C has the same magnitude as A. And okay, I already said that in this case, A is equal to D as well, which is just a repetition of what we saw before. But what about here? Here you go. You know, vectors can be multiplied and divided by scalars. Okay, let's say This scalar C here is a number that's greater than 1. So it means that the length of E is going to be greater than the length of A, right? And similarly, let's say A here is less than 1. Then the length of F is going to be shorter than that of A. Okay? Multiply it and divide it by scalars. Okay, here's just multiplication, right? But you can also have division, which I didn't illustrate here. But if you multiply a vector by the negative number, you just change its direction by 180 degrees, right? So here you go. If you multiply a vector by a negative number, you change its direction by 180 degrees. That's what that illustration is all about. Pi plus theta. You have theta here, you have pi plus theta. Okay, here you go. The vector multiplied by a positive number and divided by a positive number. Half the length, twice the length. I don't need that. Vectors A and B, you know, vectors can be summed, just like you saw before, right? We did the summation only for vectors that are different, for vectors that were equal, right? I showed an example of the sum of two vectors that are equal, but you can also sum two different vectors, okay? You can have A plus B. In other words, you can have A plus B. How do we sum vectors? Okay. We represent the summation of two vectors by, graphically, right? Graphically, we represent the summation of two vectors by the head to tail method, or tail to head, right? Head to tail or tail to head method. In this method, you line up, you touch, right? Touch the head of one vector to the tail of the other one. The resulting vector is the one that is drawn from the tail of the other vector, or from the tail, from the free tail to the free head, right? So here we go. We have vectors A and B. I want to sum A with B. What do? I put the head of one vector to the tail of the other one. Okay, it works the other way too. I put the head of the vector B at the tail of the vector A, but it works the other way as well. Okay, and the final vector is drawn from the head of B to the tail of A. But you can do the other way as well. You can put the head of A at the tail of B. And the resulting vector is going to be exactly the same one that you got before. Same magnitude, same direction. Vector C. Okay? Vector C. So vectors obey what we call the commutative property. Now, in summation, vectors are commutative. Vectors obey the commutative property. In summation, as well in subtraction, right? As well as in subtraction. Vectors obey the commutative property. Here we're doing just the one-dimensional example, but we can come up with the two-dimensional example as well. A and B, they're not collinear, right? But they can also be summed up. Look, A and B, head of the A to the tail of B. Resulting vector goes from the tail of A to the head of B. Okay? Very important method. I want you to memorize that. There's another method too, but the head to the tail method is the most important one, the most powerful one, okay? The head to tail method works all the time from one-dimensional vector and two-dimensional vector. The other method doesn't work all the time. The other method works only for two-dimensional, for vectors in the two-dimensional space. So that's the head to tail method. You know, I need you to practice that over and over again. It's not difficult. Go. Make those vectors look nice here, right? There's a brown arrow there at the top of the, I do not know why the software does that. Software, for some reason, put the vector in the brown color. The arrow there in the brown color. One-dimensional summation of vectors, right? The other method doesn't work for one-dimensional summation of vectors. Okay, so here, I'll start. And you can do the other way too. You can do B plus A, right? B plus A means that B comes before A. Go. Oh, here, what we have here is the other method that I mentioned to you. The other method that is not as powerful, but it can be more convenient under certain situations. That's why we teach that too. That's the parallelogram method. In the parallelogram method, we put the tail of the one vector with the tail of the other vector. Okay? And then we draw a parallelogram out of this drawing that you see, out of this configuration that you see. Okay, this parallelogram is going to be parallel. The sides of this parallelogram is going to be parallel to the other vectors, because that's what we are doing here. So we, on the other side, we put the B vector, right? Opposite to the side of the B, and opposite to the side of the A, we put the A vector again. We repeat. We make a parallelogram out of those two vectors. And then what do we do next? We connect this corner here of the parallelogram to the other corner. Here you go. That's what we have right now. Okay. I'm going to copy this one and paste right in here. And all I have to do is okay, next. Delete, delete, delete. Let's do that again. Here you go. Parallelogram method. Here's the head to tail method, right? Here's the parallelogram method. A and B line up their tails. Draw a parallelogram out of those two vectors and connect the corner, one corner to the other. One corner at the tails to the corner at the heads, at the two heads. Okay, so commutative property. Graphically, we represent summation of by the head to tail or tail to head method. In this method, that you line you touch, you touch the head of one vector to the tail of the other one. The resulting vector is the one that's drawn from the free tail to the free head. There is also the parallelogram method. Okay. Well, okay, how do you do that? Line up the tails of the two vectors, right? Draw a parallelogram of these two vectors. Connect the two tails to the vector, the two heads. That's just a summation. This, the subtraction of the vectors is done in a similar way. I already discussed that with you, right? So what is the subtraction of the two vectors, right? Subtraction of the two vectors is nothing but the summation between one vector and the negative of the other one. It's like that. Here you go. Plus, oops, roots, writing here, like that. So in order to come up with the subtraction of two vectors, all you have to do is to get the summation of A with the negative of B. Okay? If A is in this direction, the negative B is going to be in this direction, and the resulting vector is going to be this one right in here. Okay? By comparison purposes, note that the A plus B is different from A minus B. Okay? When you, here you go, to subtract two vectors A and B, which is A minus B, comma, you must sum A with the negative of B, or A plus parentheses negative of B, right? You draw the A vector, draw the negative B vector, and then use the tail to head method or the parallelogram method, either one. Okay, so here you go. Tail to head method, right? Here you go, one dimensional. You cannot use the parallelogram method in the case of one dimensional vectors, okay? But we teach it anyway. Now, okay. Here you go. What you see right in here is the representation of magnitude of a vector. Representations, useful representations. Right now, let's talk about useful representations of vectors. You already know that one of the representations of vector is the letter with the arrow at the top. Letter, that's one of them. Letter with the arrow at the top. Okay. The magnitude of a vector. So we have another representation. The magnitude of a vector is represented by magnitude of a vector A is represented by something like that. Okay. The magnitude of the vector is a scalar, right? So I'm going to put the scalar equal to A. This scalar being equal to A. Okay. Or even better, capital A. Capital A. So let's say, here you go. We have a magnitude of vector A is 3 units. Magnitude of vector C is 1 unit, right? However, when we sum those two vectors, the magnitude of the resulting vector is not going to be 4, it's going to be 2, because one of the vectors has the negative direction. Okay? That's the vector C. That's the vector A. This one is the vector A. I'm going to put that in different colors so you can distinguish better. You got? That's red, right? This one I'm going to put it in blue. So now it's clear, more clear, right? Red. And blue. Okay. But if we subtract those two vectors, if we subtract those two vectors, A and C, right? Now you're going to get a larger number, right? Because I'm inverting the direction. That's a funny, way of adding and subtracting vectors. Okay. One more. Here you go. Now, note see that one, okay, so here you go. Let's put the summation. One more important, the summation of two vectors may have a magnitude that is less than the subtraction of two vectors. Okay. How do we find now? How do you find the magnitude of a given vector, right? Well, there are two techniques. That's what we're going to do next. Okay, so here you go. Consider a vector A that has two units, and you know the angle that this vector makes with the horizontal direction and the vertical direction, right? Okay, this magnitude here can be thought as being, this magnitude here can be the square of this one plus the square of this one, taking the square root, right? Notice that we have a right angle triangle right in here, right? So here you go. So here's the, oh, I'm sorry. What we have here is the following. We have the vector C, right? Let me just fix that. And we have also the vector A. I'm gonna put that in red color, just like we did before. In this specific case, the magnitude of C is 1 unit and the magnitude of A is 2 units. When we sum those two vectors, we end up with this resulting vector here, A plus B, right? And I'm gonna put it here, A plus C, sorry. That's the A plus C vector. Nope. Copy and paste A plus C vector. Right here. The magnitude of the A plus C vector is given by the square of one side plus the square of the other side and the square root of it, okay? Here too, here's the subtraction of two vectors, right? We did that before. Two vectors that are perpendicular to each other. So it's easier to sum vectors that sum and subtract vectors that are in one dimension. It's easier. If the vectors are not in the same direction, but at different directions, right? Then it's a little bit more complicated because it requires a different equation, right? Here you go. And here is the summation, right? The vectorial summation. There is one more, okay. What if the two vectors are not perpendicular to each other, right? What if the two vectors are not perpendicular to each other? Let's document here first. How to find the magnitude? How to find magnitude of the summation of two vectors, right? Of the summation of two vectors, right? 1. Well, the answer is there are 3, the summation and subtraction of 2 vectors, right? There are 3 different possibilities. 1, collinear vectors. Vectors that are perpendicular to each other. And 3, vectors that make an angle with each other. Okay. Here is the example of collinear vectors. Here is the example of perpendicular vectors. And here is the example of 2 vectors that make an angle with each other, right? So here we go. We know that the resulting vector can be obtained in terms of the head-to-tail method, but then we have to figure out how we can get the magnitude of this resulting vector. Okay. In the case of 2 perpendicular vectors, right, all we have to use is that the Pythagorean theorem. Okay. Whereas in this case, you use the cosine law. I'm going to put it between quotes, law. Okay. This law is not difficult to memorize. The Pythagorean theorem, don't forget the Pythagorean theorem is a special case of the cosine law. The Pythagorean theorem is a special case of the cosine law. Okay. So going here, let's see. Okay, here you go. Consider this triangle here. Sides A, B, and C, right? The angles opposite to those sides have angles alpha, beta, and gamma. Alpha is perpendicular to side A, beta is not perpendicular. Alpha is opposite to side A, beta is opposite to side B, and gamma is opposite to side C. Okay? There's a relationship that's very easy to memorize, right? For this cosine law, consider a triangle of sides A, B, and C. A, B, and C, and angles alpha, beta, and gamma. Alpha, beta, and gamma. Let's see. Nope, that's not gamma, that's chi. Must be, yeah, alpha, beta, and gamma. These angles are opposite to their respective sides, right? Alpha is opposite to A, beta is opposite to B, and gamma is opposite to C. Accordingly, according to the cosine law, we have the following relation. It can be derived, okay, I'm not going to derive it here. And it's not difficult to memorize it. And let's not forget, right, that A is square. It's very similar to the Pythagorean theorem, okay? This is the Pythagorean theorem part, okay? But then we have another term. It's going to be 2bc. We must have a negative number here, right? And what? Cosine of alpha. Like that. Okay? Let's see if we have it here. No. Yeah, we do not have the Pythagorean theorem, the cosine law here. But it looks just like that. Let's test. Let us test this relation. Let's test this relation. Okay? Let's test the relation to see if it works or not. Let's test this relation for special cases, okay? Okay, the first special case is the one in which, here we go. I'm gonna copy this one. Okay, here. The first special case is the one in which this vector, right? Which is vector C, is lined up with vector A. Okay. Vector C is lined up with vector A. A is 2, C is 1. So the resulting magnitude should be 3, right? Let's write it down. For this special case, I have to ungroup. Yeah, here you go. Now I have it. No, doesn't work. Okay. The resulting magnitude is supposed to be 3. Like that. Oh gosh. It doesn't cooperate, does it? So the magnitude is supposed to be 3. Right? So if we were to make it a triangle of this guy, right? If you were to make a triangle of this guy, the resulting, I'm gonna exaggerate a little bit here. Exaggerate. Don't forget, they're collinear, but I'm exaggerating the fact that, so we can use the cosine law, right? Here's my D vector, and this angle here for collinear cases, this angle here, this angle opposite to the side is going to be 180 degrees, right? So let's do that. Here we go. I'm going to for the ACD triangle, ACD vectors, for the AC collinear vectors forming a D vector, we have the following, right? The D here square is going to be equal to the A square plus C square. I'm gonna put it capital letter instead of lowercase. D square, A square plus C square, 2AC, and cosine of delta, right? Delta is the angle opposite to the side D. Delta in this case is going to be 180 degrees. Oops. Yo. What's going on here? Oh, it doesn't do it. What a shame. Huh. Let's try it again. Ah, strange. Yeah. Cosine of 180 degrees is -1, right? I'm gonna put -1 here. -1. Okay. -1 multiplied by this negative sign is minus. Turns out to be plus. And what you end up having here is A plus C squared. A plus C, okay? In this case here, I made A, okay, equal to the magnitude of the A vector. I represented the letter A equal to the magnitude of the A vector, the letter C equal to the magnitude of the C vector, and the letter E equal to the magnitude of the D vector. Like that. Okay, and now we have the following. D squared is equal to A plus C squared. D is equal to A plus C, right? Like that. Make sense? We're testing. We're just testing. Well, since A is what, 2, right? And C is 1, we get the numeric value 3. Just like we had predicted before through a different method. What's that? Here. Now we can do the other way as well. What if we have the vector C along the other direction, right? What if we have the vector C along this direction here? We still have magnitude of C equal to 1, magnitude of A equal to 2, but now the resulting vector, we go, that's A and that's C. And that's C, right? But now the resulting vector is going to be something like that. The resulting vector D. In this case, A plus C is going to be 1, right? Let's see if it works as well. Okay, so we go ahead and represent those two one-dimensional vectors as you know, as making a small angle with each other, right? Making a very small angle with each other. This angle that you see right in here must be equal to 0. Consequently, this this angle here, which is opposite to the resulting vector d, resulting vector d, this angle here must be equal to 0, right? That's how we look into that. As this angle goes to 0, vector c becomes anti-collinear. Becomes collinear, but in the opposite direction, right? That's how you visualize it. This angle. What time is that? 11:57. We are testing the other one. Here you go. Now, let us now testing. Let's now test this relation for the special case in which A and C, in which A and C are anti-collinear vectors forming a vector, forming the vector. What are going to have? Now this delta here is going to be 0 degrees, not at 180 degrees like we had before. And this value here is going to be a positive 1, right? This sign is going to be negative. We get A minus C negative, and minus. Finally, 11:58, we can do that for 90 degrees now, right? Let us test this relation for the case in A and C are perpendicular vectors, right? Let's take a look here, which would be, what I'm gonna do here, I'm gonna copy that, right? I'm going to make it collinear. Yeah, this one here. Hey. That's the trick that we do to figure out the angle, which is not obvious, right? Now the next one is, let's say, I'll use this one for two vectors that are perpendicular to each other, okay? Now A and C perpendicular to each other, right? Should be square root of 5 is 2 square plus 1 square is 5. Take the square root of 5. And the equation, we're almost done here. Let me do that and then we can go home. Right, let's see the cosine law. Perpendicular vectors for, okay? So here you go. Now the angle delta, let's take a look at the angle delta. The angle delta is going to be this one here, 90 degrees, right? 90 degrees. 90 degrees is what? This cosine of 90 degrees is 0. Consequently, this term disappeared, right? And we get the Pythagorean theorem. We get the Pythagorean theorem. Yep, do that here. It goes. This one is erased. Square root here. Okay. So end up with square root of 5. Do this one like that. Here you go. So we are done here now. Any questions? So I see you on Wednesday, right? I'll be here. Don't forget I have office hours right now. If you want to ask any questions, I'll be around for another hour. So see you on Wednesday. Okay. Okay. Go ahead, Camden.
Hello, can you hear me?
Yeah.
It's about the homeworks and stuff. So I would like to ask you these questions on like office hour. Is that okay?
Yeah. Okay. So you are doing the homework and you have some problems that you are having difficulty with. Is that right?
Yes.
Okay. And let me go there. Which one? Which homework? 1, 2, 3.
It's from chapter 2. I can actually share my screen if you
Okay.
give me permission to do it.
Okay. So let me start. Hang in there. Stop sharing, and then I'll go ahead. You can share the screen.
Okay. Thank you. Where's the sharing screen? Oh. Yeah, so is this problem?
Friend attempt in progress. Okay, the lost drone. What does he want? You and your team explore the edge of Antarctica mountain range and you send a drone ahead to help navigate. Take off, you lose sight of the drone, and a few seconds later, the controls malfunction. The drone stops sending visual image and navigational information set for speed and directional data. Changing speed directly, the drone heads west until it makes a drastic turn at the 5 minutes mark. Beta is 45 degrees, so after nearly 10 minutes, the speed drops to 0 and the drone stops sending data. It has crashed. Okay, how far is the drone from you? Okay, this one here. Okay, this one here requires a vector. Requires a vector. Oops.
Oh, should I stop sharing?
No, don't stop sharing.
Okay.
But okay, good. So what's happening here? As time goes by, that's the velocity, right? You and your team are exploring the edge of Antarctica mountain. Okay, so let's do that. Don't stop sharing yet.
Okay.
What did you try to do?
So this is what I did. I try to, so for my first attempt was like getting the average velocity first, and then just try to yeah, the first one, that's what I did. And then I did the, what's that called, distance. It goes velocity times time plus 1/2 acceleration law, but didn't work. And then second attempt, I did like half and half, west and east of south. but
Yeah,
I have no clue like how to do this problem. So
yeah, okay. This problem is a two-dimensional problem, okay? We're start covering it right now. That's why you haven't been able to solve it. Okay, so let's see here. We can do that together. And
okay.
so for this problem, for you to solve this problem, you have to make a drawing. Okay, did you make a drawing?
Yeah, I'm on it.
Okay. So here we go. Okay, the situation. Now let me share the screen with you.
Okay, I'm gonna stop sharing.
Okay, lost drone. You and your team and explore. So this, okay, after takeoff, changing speed directly, the drone heads west until it makes a drastic turn. Okay, so here we go at the 5 minute mark, right? 5 minute mark is what, 300 seconds.
Right.
Okay? At 300 seconds. Okay, so he kept on moving west. Okay,
Right.
until 300.
That's negative, right? Negative.
Oh, we're gonna get there. We're gonna get there. Let's
Okay.
not worry about the number yet. Okay, that's it's west. West is to the left, right? And then let's see, east 45 degrees east of south. East of south. Okay, east of south is going to be like that. Okay,
Right.
east of south. You are initially here. There where the drone was initially. Okay. So after nearly 10 minutes, the speed drops to 0 and the drone stops sending data. See, this is a two-dimensional problem. Okay. We didn't cover that yet. Using the speed directional data, the team draws up the graph shown below. Okay, the drone is, so what you have to do, you have to calculate this distance here. That's what you have to do. You have to wait a minute. You have to calculate this distance. You have to calculate this distance. And then after those two calculations, you calculate this one. This angle here is how much this angle here?
I think that's 45.
That's right. So you put 45 degrees there. Right? 45 degrees. 45 degrees. Superscript. But now you have to calculate that. How do you calculate that? He's flying west, right?
Yeah.
He's flying west until here.
So I have a question. So initial velocity is 10, right?
Yes, 10 meters per second for what? 50 seconds.
Okay, so that's like when you actually apply the formula to get the velocity delta velocity, is it 10 plus 15 over 0 plus 300, or do I need to just like do it by grid? I that's the thing that I couldn't get to.
Okay, so 10 meters per second for 5 seconds, right? 10 meters per second times 5 or 50? No, it's 50, sorry. 10 meters per second times 50 seconds is 500 meters, right? Here's 500 meters, right? Now, what about here? Here is this area. Okay. This area is going to be what? 50, right? Times, no, wait a minute. This side here, 17 and a half, plus this side here, 10, 27 and a half. 27 and a half times 50 divided by 2, okay?
Okay.
And so we found this displacement here, we found this displacement here, Now you gotta get this displacement here. 100 times 17.5.
So I cannot just do 10 miles seconds I mean what's the other one? The 15 miles seconds. I mean meter seconds minus 10 meter second like that. That's not
No.
correct, right?
No,
Okay.
you have to calculate this whole area here.
Oh, okay.
This whole area is going to be the displacement in the
Can you
west
show me the
direction.
formula by
Yeah,
any chance?
yeah, we're doing that right now. Let's see.
Okay.
Lecture, this one right in here. Okay. Okay, problem. Do you have the problem? Homework, right?
Mm-hmm.
Homework problem. Okay. From 0 to 300 seconds, 5 minutes, right?
Mm-hmm.
The displacement of the drone was, okay, you know, 50 times 10, right? This area, 50 times 10 meters plus 17.5 meters per second plus 10 meters per second. Okay, is this side plus this side? This is a, you know, trapezoid, right? This height is 50 seconds divided by 2, right? So, and that's the air, that is this area here. Now this area is 100 times 17 and a half, 100 seconds times 17 and a half, 17 and a half meters per second. Okay. Plus, now this area here, this area is different, right? That's gonna be 17 and a half plus 12 and a half, 17 and a half meters per second plus 12 and a half meters per second. This side plus this side times this one is 100, right? No, it's 50 times 50 seconds divided by 2. And finally, the other one, right? 12 and a half plus 15. 12 and a half plus 15, that is meters per second, times height, 50 seconds. 50 seconds divided by 2. So that's the sum.
Professor, but why do you have to divide it by 2 when
Well,
you
because this is a trapezoid. Remember the equation of the square of the area of a trapezoid is what? You know, large base divided by a smaller base.
Oh,
height divided by 2.
So you need to apply the geometric formula as well, like when it comes to this kind of problem. Oh, okay.
Yeah. The displacement here is equal to this area. The displacement here is equal to this area. The displacement here is equal to this area, and so on, right?
Oh, okay.
Okay.
Oh, okay.
And then you do the same here. So with this equation, we find the first displacement, the length of the first displacement. Now you have to do the same for the displacement here, right? Area here plus area here plus area here, right? Okay. 1, 2, 3, 4 areas. Okay. Once you find that, once you find this area here, once you find this area here, you find this one. Once you have those two sides, then you determine what's the value of this side here.
So when I finally find the both value from the graph, do I need to use Pythagorean theorems to get the other side?
No,
No? Okay.
you use the cosine law.
Oh, cosine law. Okay.
Yeah, because it's 45 degrees here. We do not know if this one is 90 degrees, right? We do not know if this one is 90 degrees. We do not know if this one is 90 degrees. Okay.
Oh, okay, okay.
So you have to use the cosine law.
Then when is the special case that you mentioned today to use
Well, the special case is like for collinear
90
vectors,
degree?
collinear vectors and perpendicular vectors.
Oh, okay.
Okay, so this one we do not know if they are perpendicular. Okay.
Okay.
We do not know if they're perpendicular. It's flying west, and then it's flying 55 degrees east of south. You know, I do not know if this angle is going to be 90 degrees. You know, if it's too short, right? Definitely
Right.
it's not going to be 90 degrees. But
So,
yeah, we do not know. Okay, we will find out whether it's 90 degrees or not, right?
so this is like displacement problem, right? Like I mean, but it's like two-dimensional, right?
Yeah, this is two-dimensional, which we started covering right now. Two-dimensional motion, which we started covering right now.
Oh, okay.
Okay. How are the other problems?
I don't know how to get the yeah, what's the B? How to get the how to solve the B problem?
V?
No, B, like the
B.
A and B.
Which B? Beta?
No, there's like a two part
Oh,
like
item
separate
B, you
part.
mean?
Yeah.
Item B?
Yeah.
Okay, in what direction must you go to retrieve it? Okay, the direction is going to be this one right in here. First, you're gonna find this one. Then you're gonna calculate this one. Once you have those two, you calculate this one here, right? And
Do I
then,
need
uh, and then once
Okay,
you have
okay.
this one, you'll be able to find out what's this angle here. Okay, you'll be able to find out this angle here using either the cosine law or the sine law, either one.
So I don't have to use the arc tangent or anything like that, right?
No, you have to use either the cosine law or the sine law, either one.
Oh, okay.
I don't see how you can use arctangent in this case, unless you have a right angle triangle. I do not know if you have a right angle triangle there.
Okay, so I cannot use tangent because we don't know if this is going to be the right triangle or not, right?
Yeah, that's right.
Okay.
If you use a right angle triangle, then yes, you can use that. But we do not know, right? We have to do the calculations to find out if it's a right angle triangle or not.
Right. And I have other question. But this is not from the homework, but I started like solving bunch of kinematic and like the chapter 1 related problem, chapter 1 and 2. And this I would like to share my screen again.
Okay, so let me stop sharing. Your turn.
Okay, let me see if this is right. So is this problem? I know how to do the A, but I don't know. I'm not too sure about the B and C because like uh this is like exactly almost same thing, right? Like
Okay, that's the average speed. The magnitude of the displacement. Yeah, the magnitude of the displacement is going to be the distance from A to F, okay?
Right.
Okay,
So
which one do you don't know to do? Which one you do not know how to do?
B and C. A is kind of easy. So
yeah, average speed 300 walk it following the route in the grid below. It doesn't say if it's average. Wait a minute, 3,550 seconds.
That's the time. So I basically use like the grid to find the average speed. But the B part is kind of like confusing me. Do I need to like just like measure um like four grades times 4 grades squared times 3 grades squared as as to to measure the displacement? I have no idea like
Well,
how to
this is just trigonometry problem, right? This is just a trigonometry problem. The
is it?
distance, yeah, the distance between A and F,
Mm-hmm.
the distance between A and F is is going to be the magnitude of the displacement. A and
Right.
F, you can come up with a right angle triangle, right?
Mm-hmm. Yeah. This one,
Right?
yes.
Okay. The side from the vertical side, that's gonna be 1.5 kilometers in the vertical
R-
direction. In the
uh-huh.
vertical direction.
Right.
Move in the vertical direction. Yeah, see, 1.5 kilometers. In the horizontal direction is going to be 2 kilometers.
Yes. Yeah.
Okay, because you have a scale here. Now that we have 2 kilometers here and 1.5 kilometers here, you can find out what's going to be the distance from NAF. ENF. ANF is the hypotenuse of this right
Mm-hmm.
angle triangle.
So it's 9.
I do
I
not,
mean
I can,
three. I mean
let's see,
3.
3. Wait a minute, it's gonna be 2 square plus 1.5 square. How did you get 3?
Wait, two and a half. Oh, I thought it was 1.5. No, 1.5
Square
square. Yeah.
plus 2 square. 1.5 square plus 2 square, take the
Oh,
square.
oh yeah. I mean 6.25.
Okay. 6.25. Did you take the square root?
Oh, I need to do the radical thing. Right. So it's 2.5. Right.
Hmm.
I mean earlier today I got this answer 6.25 and I didn't use the radical sign. But the thing is like there's like an answer sheet
Uh-huh.
as well. But it was telling me the like whole different thing. That's why I'm like here to ask you.
Uh-huh.
Um
Let me
and
see.
then
I can do that for you. Let me share my screen with you. Hang in there. Do not turn it off yet.
okay.
I'm gonna copy and yeah, it looks like it's 2.5, like you said, right?
Okay. Yeah, so number C is like just use the unit conversion, which is like 2,500 meter over 3,250 second. That should be the C answer, right?
Okay, a magnitude of the average velocity. I didn't do the math yet, but it's gonna be the distance from A to F divided by 3,250. Okay.
200, yeah.
The average velocity is going to be smaller than the average speed.
So it's about like 0.7692
I
meters.
didn't do the math yet, so I do
Uh-huh.
not know if this. You have to know the distance from A to F, right?
Yeah.
You calculate, right, the distance from A to F.
Yeah, I think distance is like 2,500 meter,
Okay,
right?
yeah, that looks like, yeah, 2.5 kilometers, yeah, 2,500 meters divided by 3,250 seconds.
Yeah. So it's 0.7692. Okay. And I have I I would like to edit today's video if you don't mind.
Okay, it's gonna take some
Um,
time, but I'll post it. Yeah.
oh no, I'm the I want to do it as an extra credit if you don't mind. Like
Okay, you wanna edit the video? Okay.
yeah.
So you know how it goes, right?
I need to just like get rid of the unnecessary part, right? Like taking break parts and
Yeah. Yeah, you can, let's see, do it for the last year's class, okay? Last year's recording.
Oh,
Okay.
last one?
Yeah, last year's recording. Don't do for what we're doing this semester, otherwise it's gonna take too long for you to do it. And do you know how to get let's see.
I don't know how to get the video.
Yeah, it's easy, it's easy. So let me see. Are you sharing the screen?
No, I'm not sharing anything yet.
Am I the one who is sharing the screen? Let's see here.
Oh, you're not sharing the
I'm
screen.
not sharing the screen at all. Okay. Okay. So, it's still recording.